Hey everyone, welcome back to the channel. Today we are going to be doing AQA GCSE Chemistry topic 1, Atomic Structure and the Periodic Table. And don't worry, I'm going to break it all down nice and simple so it actually sticks, and I'll throw in a few tips that might save you some stress in the exam. And just before we start, our TikTok handle is at _9stars for more study content. So let's start right at the basics. What is an atom? Atoms are the tiny building blocks of everything around us, you, me, your phone, even the air. It's all made up of atoms. Inside an atom, we've got three main particles. We've got the protons, which have a positive charge of +1 and also a mass of +1, neutrons, which have a zero charge, no charge, and also having a mass of 1, and electrons, a -1 charge, which have a negligible mass, which is really close to zero, but it's not zero. You do not need to know the fine detail for this, you will learn this at A level in more detail. And think of protons and neutrons essentially chilling in the nucleus, like that's the atom's core, and then the electrons whiz around the outside in shells. And there are two really important numbers we have here, the atomic number and the mass number. So the atomic number is essentially the number of protons, and the mass number is the number of protons and neutrons. So that's going to be key later when we look at the periodic table. Next we move on to isotopes. So essentially it sounds fancy, but it's actually pretty simple. Isotopes are just atoms of the same element that have the same number of protons but different numbers of neutrons. For example, carbon has two famous isotopes, carbon-12 and carbon-14. Both have 6 protons, but carbon-14 has a couple of more extra neutrons. So in this diagram here, you can see that they all have the same number of protons, 6, but what actually varies is the number of neutrons. So essentially the chemistry is the same of them, because it's the protons and electrons that decide an element's chemical properties, but the mass is different, which can make isotopes useful in stuff like carbon dating. We'll see isotopes pop up later when we talk about the periodic table. Now, electrons. These little guys are key to how atoms actually behave. Electrons are arranged in shells around the nucleus. The rule is the first shell, you have a maximum of 2 electrons. The second shell, you have a maximum of 8 electrons. Third shell, maximum of 8 electrons. And here's the important part. The way electrons are actually arranged, the electronic structure decides how that element reacts. So if an atom's outer shell is full, like the noble gases for example, it is super stable and unreactive. If it's missing one electron, like the alkali metals, it's itching to react. So in order for it to gain that electron. We'll talk more about this when we get into groups 0, 1 and 7. Now, this is something that a lot of people struggle with, the development of the atomic model. So the atomic model didn't just pop into existence one day. Scientists built it step by step, and you need to know who these scientists were and what they created. So essentially we'll go in chronological order, starting with John Dalton. Dalton said atoms were solid little spheres and they can't be divided. Simple, but wrong. Then Thomson came along with the plum pudding model. He thought atoms were a big positive sphere with negative electrons dotted inside, like raisins in a cake. And then Rutherford tested this with his famous gold foil experiment. He discovered atoms have tiny positive nucleus in the center, and most of the atom is empty space. Huge update. And then Bohr added that electrons aren't just flying anywhere, they're fixed in shells. They're fixed in shells at set distances from the nucleus. And then finally, Chadwick discovered neutrons, which explained the missing mass. So here I've actually created a diagram which shows you the evolution. It does miss out Bohr, but Bohr's is really minor. It just states that electrons were then put into shells, which essentially fixed distances from the nucleus. So the model evolved as experiments got bigger, and that's a big theme in science. Evidence changes theories. Okay, now we are going to look at what atoms look like, and let's zoom out to the periodic table. The periodic table is basically the cheat sheet of chemistry. It's organized by atomic number, so each element is in order of how many protons it has. It's split into groups. The vertical columns, all the elements in a group have the same number of electrons in their outer shell. That's why they behave in similar ways. So groups as in vertically going downwards. So lithium, potassium are all in the same group. And then we have periods, which are the horizontal groups. Not groups, but rows. That tells you how many shells of electrons an atom has. On the left, you've got mainly metals. On the right, you've got non-metals. And in the center, in the middle, you've got the transition metals. This layout is going to make a lot more sense once we start looking at specific groups. So let's start with the chillest group on the table, the noble gases. They're in group 0, which means they all have a full outer shell of electrons. That makes them super stable and basically unreactive. They are colorless gases at room temperature, and their boiling points increase as you go down the group. So helium at the top has the lowest boiling point, and as you go down to xenon, over here, it goes up, as shown in this diagram. Because they don't react much, noble gases are useful, like helium in balloons, neon in lights. They're basically chemistry's introverts. Now let's talk about the opposite of chill, the alkali metals. These are the ones in group 1. Each alkali metal has one electron in its outer shell, and because atoms are desperate to get a full outer shell, they want to just get rid of that one electron. That makes them super reactive. They react with water to give hydrogen gas and an alkaline solution, which is where the name comes from. So lithium, sodium, potassium, drop them in water and they fizz. They move around and they give off hydrogen. Potassium can even catch fire. And here's the trend. Reactivity increases as you go down the group. So sodium is more reactive than lithium. Potassium is more reactive than sodium, and so on. Why? Because the outer electron is further away from the nucleus and less strongly attracted, so it's easier to lose. These guys always form the +1 ions in compounds like Na+ or K+. You'll see that a lot in exam questions. And here's a little diagram showing you the electron being transferred to make an ionic compound. Now, next up, the halogens in group 7. These are kind of the opposite of group 1. They've got 7 electrons in their outer shell. That means they're desperate to gain one more electron to make a full shell. Halogens exist as diatomic molecules, like chlorine gas would be Cl2, bromine gas is Br2, and iodine is I2. So they always come in pairs. Here's their trend. The reactivity decreases as you go down the group. Chlorine is the most reactive, then bromine, then iodine. Why? Because as you go down, the outer shell gets further from the nucleus, so it's harder to attract that extra electron. They react with metals to form halide salts, like sodium chloride. Sodium chloride is table salt. And displacement reactions are super important here. A more reactive halogen will kick out a less reactive one from a compound. For example, chlorine, Cl2, can displace bromine from sodium bromide because chlorine is more reactive than bromine. Make sure you know this and you're able to apply this for exams. Next, moving on to transition metals, which live in the middle of the table. These are your classic metals like iron, copper, nickel. They've got a few special properties. They're good conductors of heat and electricity. They're strong and malleable, meaning that they can be hammered into shape. They form colored compounds like copper sulfate being blue. However, that does go a bit into A level, but it's good knowledge to have. And they can also form ions with different charges, such as Fe2+ and Fe3+. We really don't see this with alkali metals, which only form a +1 or a +2. Transition metals can form many. So, as I said, iron +2 and 3+. And they're also often used as catalysts, which speed up reactions without being used up themselves. For example, iron is used in the Haber process to produce ammonia. So while groups 1 and 7 are all about reactivity trends, transition metals are all about practical uses. And here's an exam question which says, which is the most likely metal in the metal oxide catalyst? We know that transition metals are usually the ones catalysts. So in the exam, I want to look at my periodic table and see which one of these is in the middle, which one's a transition metal, and take the correct option. So in this instance, it would be vanadium. Nice, easy stuff. Okay, so let's do a quick comparison, metals versus non-metals. Metals tend to form positive ions because they lose electrons. Non-metals form negative ions because they gain electrons. Metals are good conductors, malleable and strong. Non-metals are usually brittle and act as insulators. This is a nice straightforward bit, but it comes up a lot when comparing elements in the exam, especially in context questions where they'll give you a table. Make sure you quote references from that table. So now we're going to have a quick go at an exam question that comes up. So the first question is, predict one observation you would see that shows rubidium is more reactive than potassium. And then the second question is, explain why rubidium is more reactive than potassium, and then completing the equation. And then D is a multiple choice question. Have a quick go at this, pause the video and come back. Okay, cool. So for the first question, the reason that it's more reactive is because it has a more vigorous bubbling and it has a bigger / brighter flame for rubidium. For the second question, why is it more reactive? So rubidium's outer shell is further from the nucleus, so there is a less electrostatic attraction between the nucleus and the outer electron. So the outer electron is more easily lost. This is the balancing equations question. This comes up a lot in quantitative chemistry topic 3, but this is the correct answer. If you haven't got this correct, I will explain how to do this in a future video. And number D, the multiple choice, was the noble gases have boiling points that increase going down the group. Great. So, and that's the end of topic 1, atomic structure and the periodic table. We've gone from the history of the atomic model to isotopes, electron shells, and then through the periodic table. If you're revising, the big takeaways are essentially know your atomic structure basics, learn the trends in group 1, 7, and 0, and remember how the periodic table is organized. So that's it from me. Thank you for watching. If you have any questions, please drop them down below. And once again, for more study content, our TikTok handle is @_9stars for more study content. See you in the next one.